Okay, we're back for part 2 of our videos on section 10.2 out of our calculus text. And I want to start off by looking at some geometric series and determining whether or not they converge or diverge or not. So we want to recall that a geometric series converges. We got the result in our text. A geometric series converges when the absolute value of the ratio is less than 1. And that's the only time it converges. And so what we want to do here in these problems is we want to focus on what the ratio is and ask, is the absolute value of that ratio less than 1 or not? If the answer is yes, it is less than 1, we know it's going to converge, and we actually have a formula for the sum of a convergent geometric series. So we want to remember that the sum of a convergent geometric series, summation n equals 0 to infinity, c times r to the n, is c over 1 minus r. Now it's going to be important for this formula to apply that n start at 0. So we'll keep that in mind as we go through things. So our first example over here, summation n equals 0 to infinity, 4 times pi over 6 to the n. Our ratio is pi over 6. We remember that pi is about 3.1. And so the absolute value of the ratio, in this case, since it's a positive number, is also pi over 6. That's less than 1, so the series converges. So this is our justification. And then the sum, c here is 4. And so the sum is going to be 4 over 1 minus pi over 6. And if I want to make this a little nicer, I can write 1 minus pi over 6 as 6 minus pi over 6, in which case, when I convert this into a simple fraction, by multiplying by the reciprocal of the denominator, I get 24 over 6 minus pi. And that's our sum. Note that if this had been summation n equals 0 to infinity 4 times pi over 3 to the n, that would diverge. And I'll ask you to think about why that would be the case. Our second example is a little bit more complicated. I've got a sum in the numerator, and that tells me that probably what I should do is I should break this up into two pieces. We have a theorem about linearity of infinite series in our section, and so I want us to note that we can rewrite this as summation n equals 0 to infinity 2 over 5 to the n plus summation n equals 0 to infinity 7 times minus 3 to the n over 5 to the n. And then I'm going to go further and rewrite both of these. I can write, I think about this, notice that 2 is not being raised to the nth power, so I can bring it out in front. 1 over 5 to the n is the same as 1/5 to the n. And then negative 3 to the n over 5 to the n can be rewritten as negative 3/5 to the n. So R1, the absolute value of R1, in our first example is 1/5. That's less than 1. The absolute value of R2 is the absolute value of negative 3/5, which is 3/5, which is also less than 1. So both converge. If one of them had diverged, then we would have said that the entire series diverges, because in order for a sum of two series to converge, both of them individually have to converge. And so now I can use my summation formula, and I'm going to get the first constant is 2 over 1 minus 1/5, and then my second one is going to be 7 over 1 minus negative 3/5, but I can write that as 7 over 1 plus 3/5. So that's going to give me 2 over 4/5 plus 7 over 8/5. And if you do some arithmetic, this is going to be 10/4 plus 35/8. I can make this 8 a little clearer. And that's going to give me 55/8 as my sum, 55/8. Next example, r, absolute value of r is absolute value of negative 3/2, which is 3/2, which is bigger than 1. So this series diverges. And then the thing that's a little bit different about this one is that n is starting at 2. So we have to be a little bit careful here and see how we need to make an adjustment. So let me write this out, the first few terms out here. And what I'm going to do is I'm going to pull out a common factor. So there's a common factor of 3 everywhere, but there's also a common factor of negative 1/7 squared. And so let me rewrite this as 3 times negative 1/7 squared. And if I pull that, I pulled everything out of this first term, so I'm going to be left with 1. And then I pulled everything out except a negative 1/7 here. And then I pulled out all but a negative 1/7 squared. And it looks like I've got my pattern established now. And so this is going to be summation. Now I start at 0, because this is going to be, I think about this as negative 1/7 to the 0 power. And then I've got 3/49 from this times negative 1/7 to the n. So I've converted this to a sum, a geometric series that starts at 0. And so my ratio is, the absolute value of my ratio is 1/7, which is indeed less than 1, so this converges. And so I get 3/49 over 1 plus 1/7. So I get 3/49 times 7/8. That goes away, and I'm left with 3/56 as my sum. So I will point out another way to think about this is, notice that 3/49 was actually the number I get when I take my term here and plug in. So if I take my starting term here and I plug it in right there for n, that is the term that wound up on top in my numerator. And so I can think about this then, if I don't start at 1, or if I don't start at 0, I can just plug this number in, get the first term. So if I don't start at 0, I'm going to get c times r to the k over 1 minus r as my sum. And so I'll ask you to sort of study this and see that's exactly what I wound up getting here. This 3/49 right here is 3 times negative 1/7 squared. But I'm happy for you to go out and do this the long way as well. And it helps me, that's how I prefer to do it myself in my head, or not when I write it out. Okay, our next examples involve another result from this section, the nth term divergence test. And the nth term divergence test says that if the general term of your series does not go to 0 as n goes to infinity, then the series must diverge. So let's look and see how that works in here. So my general term in this first example is 3 to the 1 over n. The limit as n goes to infinity of 3 to the 1 over n is going to be 3 to the limit as n goes to infinity 1 over n. Using one of my limit properties from the previous section, I get 3 to the 0 equals 1. That's not 0. So by the nth term divergence test, this series, make that look a little better, 3 to the 1 over n diverges. Then we've got a couple of more examples of this down here. A sub n is n squared over 2n squared plus 6n plus 1. The limit as n goes to infinity of a sub n. In this case, we could divide both numerator and denominator by n squared, or we could rely on what we know. We looked at a similar example in the last section. This is going to be, well, if I divide by n squared in both numerator and denominator, I'm going to get this, and so my limit is 1/2, which is not equal to 0, so the series diverges by the nth term divergence test. And then our third example, a sub n is minus 1 to the n of our expression in the previous case. And I'm just getting this in front of you to remind you that when we've got an alternating sequence like this, if the limit of the absolute value of the term is not equal to 0, then the limit of the sequence does not exist. So since the limit of the absolute value is not equal to 0, then the limit as n goes to infinity of minus 1 to the n squared over 2n squared plus 6n plus 1 does not exist. And so the series as given diverges by the nth term divergence test. And we'll come back and do part 3 in just a few minutes.